In our last lecture, we had a quick introduction to resolution, but only in the propositional case. We also saw DPLL, which turns out to be extremely powerful, but again, it only works for propositional logic. So, what do we do about quantifiers? And in particular, the problem of these so-called witnessing terms, that is, if we want to show that there exists something, how do we come up with the actual term, which is the thing that exists? Or if we have a universal quantifier, how do we come up with the terms to plug in to make specific instances of the property that holds universally? The original thing they tried in 1962 was basically to guess. So you need a term, you look at all the terms floating around in your problem, and just plug them in willy-nilly. That didn't turn out to be very successful, although it turns out today there are still some reasonably successful attempts of getting this to work. The big thing that happened in 1965, thanks to Alan Robinson, is what he termed unification. So we'll be covering in this lecture the journey from propositional logic, propositional resolution, to the full story of how real resolution works, including unification. From a purely logical point of view, our task is to reduce a problem stated in first-order logic to a problem stated in propositional logic, the latter, of course, being decidable. And here on this slide, we list all the stages of the process. The first involves transforming the problem into negation normal form. The next is a thing called skolemisation, in which we remove the quantifiers. I have mentioned already that for clause methods, our transformations do not necessarily preserve the meaning of the formula. And here is one place where this happens. So skolemisation preserves only the satisfiability of the set of clauses. Next, the mysterious world of Herbrand models and Herbrand theorems. Herbrand models allow us to concern ourselves only with possible canonical models of our set of clauses, as opposed to all conceivable mathematical models. Then, through Herbrand's theorem, it turns out that any explicit contradiction that we want to find to prove unsatisfiability will in fact be have finite form and consist of a finite combination of instances of our original clauses. And finally, the process of discovering these instances, finding the terms to plug in for the variables, will be done for us using unification. Then we combine unification with our previous resolution rule, which, as you recall, was propositional. Then we will get the full first-order resolution rule. So what is skolemisation? Well, first of all, it's named after a logician named Thoralf Skolem. And if you do something important in logic, maybe you will have a logical process named after you as well. Skolemisation for us involves getting rid of the existential quantifiers in a formula. We start with negation normal form because we don't want negation symbols and implications lying around all over the place where they can complicate things. With negation normal form, the negations are only applied to propositional symbols, or I could say to atomic formulas. So in particular, there are no quantifiers within the scope of a negation symbol. Now, I have written our typical formula like this, as you see here on the slide, as a nested thing that has inside it some existential quantifier, and above it universal quantifiers. This sort of thing is usually presented to people with all the quantifiers pulled to the very front of the formula in a neat string, so that you then have for all, followed by exists, and then it's very easy to see that that is the first exists in the string, and that's the one you will be operating on. That is so-called pre-next normal form. The problem with doing that is it makes the problem super exponentially more difficult to prove. So we're not going to do that. We're going to leave the quantifiers where they naturally belong, deep inside, and assume that you as computer scientists understand the notion of nesting structure, so that this thing has a for all, within it a further for all, within it a further for all, and finally there is an exists, and this existential formula is the outermost existential formula, that is, it is not enclosed in any other existential formula, so that is an occurrence that we can remove by Skolemisation. And all we're going to do is plunk in a function symbol there. It looks too stupid to be true. We have for all x1 up to for all xk exists some y, and we're going to say that the y which exists is simply f of x1 up to xk for some new function symbol f. So a function symbol that has never been used anywhere else in the problem. Having done this, you see that our existential quantifier has gone away. Now, in general, there will be other existential quantifiers in the problem, so we need to keep doing this until they're all gone. Here's a teeny tiny example. I hope you recognize the formula here. It is similar to ones we have seen before. It looks a bit implausible because it's saying there exists some x such that if p of x is true, then p holds for all values. So a rather paradoxical looking formula, which is in fact valid. When we convert it to clauses, this is what we might get. There are different ways of doing it, in fact. But here we negate it. There. This is where I wish I had my second projector and I would do it in front of you. So just imagine I am doing this in front of you. I put a negation symbol in front, and I remind you how tragic it would be on an exam if you forgot to do this step. Then we push the negation symbol inside, and now we have negation normal form. Now we look at the quantifier structure and we see we have an existential quantifier enclosed in a universal quantifier. So we invent a new function symbol, f being an excellent choice, popping that in here, and now we have Skolemized it. Now what we do, we throw away the universal quantifiers. So as the last stage of this, once you've got rid of all the existential quantifiers, you throw away all the universal ones. Finally, we are left with these two clauses. It's very important that you know what clauses actually mean in logic. So this is a unit clause. It has a variable x, and all variables in a clause are implicitly universal. Very important. Implicitly universal. This clause says for all x, p of x. Over here, again implicitly universal, and incidentally, because it has implicitly a universal quantifier, that also means this is a local scope, so I could rename this x to y if I was worried about getting into a clash with that x over there. This clause here is saying for all x, p of f of x is false. So if you are still awake, you'll note that in fact these two clauses are contradictory. And if we can only think of an effective way of revealing the contradiction, then we will have a proof that this negated goal is unsatisfiable, and therefore that this formula at the top is a theorem. Why is Skolemisation correct? Well, let's try and argue this mathematically for the very simple case of for all x exists y, a. So what does it mean for this thing to be satisfiable? Remember, satisfiable means there is a model of the formula, an interpretation in which it is true. So let's write the interpretation like this. With the script I, we have a domain, a non-empty domain of values, and we have an interpretation of the various symbols in A, in the formula A. Now, as usual, semantics generally boils down to translating symbols into English. So if and only if, for every x in our domain D, there exists a y in D, such that A holds for those particular values of x and y. X and y are, of course, free in A. And now we are using the fact that this relationship for all x exists y indeed suggests the existence of an actual function from D to D. The reason I've put a little hat on the function is because I want this to refer to an actual mathematical function, whereas f itself is merely a function symbol, the symbol denoting this f hat here. So this f hat is exactly the function that maps the x's and d's to the y's and d's. Finally, if you substitute syntactically fx for y, where f now is the symbol, then this will be true and an interpretation I prime, which has been extended from I by making the symbol f denote the actual function f hat. But for this thing to hold, for all x and d, of course, for this to hold is exactly what it means for this formula at the bottom to be satisfiable. And that is why Skolemisation preserves satisfiability, and as I've been repeating a couple of times already, preserving satisfiability will be enough for us because we are only interested in the question of whether our set of clauses is satisfiable or not. Now we turn to one of the trickier aspects of the whole business. Remember, satisfiability means a model exists, and there are an awful lot of models out there, including many things that are duplicates. So if I have a model in which the domain is the states of the USA, well, there are 50 states, and honestly, there is no difference between such a model and another model in which we have the integers from 1 to 50. So how do we avoid dealing with all these duplicates? It turns out we can construct canonical models so that for every set of clauses we can create one single unique model, provided a model exists to begin with. In other words, our construction will be, give me mathematically an arbitrary mathematical model of the set of clauses, some arbitrary set, arbitrary functions interpreting all the symbols. Then we can create a canonical symbolic model behaving in the same way as the mathematical one. Now, what is the point of this? The point of this then is that if we are interested in satisfiability, we only need to be interested in the existence of these canonical models, and we can forget that the other mathematical models even existed, because these canonical models will satisfy the same set of clauses as the original model did. So here comes some fairly hairy-looking mathematics, but really there's not a lot coming on. So we begin with a set of clauses. I must stress this construction requires a set of clauses to begin with. The whole thing is driven by the vocabulary of your set of clauses. First of all, we need your constants. If you don't have any constants, we need to throw one in. The letter A makes a good choice for a constant symbol. The reason for throwing one in is that otherwise we would get an empty model, and those are not allowed. Once you have your set of constants, you build up all your terms in layers. Now I know this looks horrible, but this is just all possible terms nested, I guess, I deep in terms of function calls. When you take all such terms, built up using all your function symbols applied to all your constants in every possible way, respecting here the number of arguments each function symbol expects, that will be the Herbrand universe. These terms are sometimes called ground terms. That means terms not containing any variables. And the semantics of a constant will simply be the constant itself. The semantics of any function symbol will be syntactic. So what do I mean? I mean in particular that some function symbol f does not have any interesting mathematical definition like you might imagine, doing some kind of matrix inversion or convolution or some mysterious mathematical process. Instead, every function symbol will stand for the function operating on bits of syntax that will stick the letter F in front of the string of arguments that it was given. Very boring, you could say, but perfect for computers. So let's suppose, for example, that our set of clauses contains two constant symbols, namely 0 and 1, plus a unary function symbol for minus, and a binary function symbol for plus. Then we see our Herbrand universe written here. We go through our constants, 0, 1. Then we apply our function symbols to our constants in every combination. So minus 0, minus 1, etc., now using plus, the four combinations with plus. Having done that, we go to the next level. So now, for example, and I see I wasn't consistent here, I should have had minus 0, actually. Then minus 1, and then finally this one here, and so on and so on and so on. Now, this might look pretty stupid to you, and you might say, isn't 0 the same thing as minus 0, and the same thing as 0 plus 0, and minus 0 plus 0, and minus 0? Are they not all the same? And the answer is no. They are all different. They are all syntax, and only syntax. So this is our canonical syntactic model that can imitate any model of the various symbols shown here. Now, predicates will behave a little differently. So the idea with the semantics of a predicate is that it will stand for, remember, a predicate is a relation taking its n arguments, and it will be true for some combinations of arguments and false for others. So the idea here for this, for the first time, I told you we wanted to have a real model around, and this is where we need it. So if you like, we use the real model as an oracle, and we say that our interpretation of the predicate symbol P, when applied to the arguments T1 up to Tn, will be true exactly if it turns out true in the real model. And it will be false if it turns out false in the real model. Now you might say, I don't actually know about any models, but that's not the point. If a model exists, then a Herbrand model will also exist. So now to treat a slightly different example, here we have three clauses. We have constants 1 and 2, and we have a binary function symbol written with a dot. And what I have done, in fact, these clauses are all satisfied by the model in which dot denotes multiplication. Now, the construction of the Herbrand universe should be obvious to you. We've seen it already. You see we have every combination of 1 and 2 combined with dots in various ways. Now, the Herbrand base is every single possible combination of our predicate symbols with the correct number of arguments. So the Herbrand base is not very interesting of itself. It is a thing from which we carve the meanings of predicates. So now here, this bottom line here is an interpretation of the even predicate given by the real model in which 1 and 2 are integers and the dot is integer multiplication. And now, if you evaluate these various things on actual integers with actual multiplication, we said, yes, 1 times 2 is equal to 2, and that's an even number. 2 times 2 is equal to 2, and that's an even number. 2 times 1 is an even number, and so on. And those are all the ones that go into this interpretation of even. And it will turn out that if you then take the Herbrand model, which is purely syntactic, and therefore the Herbrand interpretation of even, which is simply this list of formulas, this also will satisfy the clauses here. Where it gets interesting, notice that if this dot actually stood for addition rather than multiplication, this clause still holds. So putting in addition here again gives us a satisfying model of the clauses, but it would give us a different interpretation of even. So where dot stands for plus, this one here, even of 1 dot 2, that is 1 plus 2 equals 3, which is not even. So for the interpretation using addition, this particular occurrence here, even 1 dot 2, would not be included in the meaning of the even predicate. From this it follows, of course this is not a proof, I'm merely sketching what the theorem says, but thanks to this construction that we have just quickly walked over, we can obtain Herbrand's theorem, which tells us that a set of clauses S is unsatisfiable if and only if it is not satisfied by any Herbrand interpretation. Now, one direction of this if and only if is trivial, because if it's unsatisfiable, then no interpretation satisfies S. But the right to left direction follows because the Herbrand interpretations are sufficient to imitate any other interpretation. And it turns out that you can show that if S is unsatisfiable, then there will be a finite unsatisfiable set of instances of the original clauses in S. So-called ground instances, meaning that we have replaced all the variables by constants. Finite, of course, means it's computable. At least we can store it. Because they are instances, they are trivially derived from the original clauses, and because they are ground, means that we are now in the world of propositional logic, and we could use something like DPLL to prove our formula, or rather to exhibit the contradiction. And this is how DPLL was originally used in 1962. So, going back to the problem we saw a few slides ago, you may remember we arrived at these clauses here. Here I have gone to the trouble of renaming the variable x just to make sure there's no idea that they were the same. And now putting in f of a in place of x and a in place of y, you can see we have now an outright contradiction between two clauses. You can see these are ground clauses. They have no variables in them, and they are instances of the original clauses of S. Okay, in that particular example, we could eyeball the problem and decide what to plug in for x and y. But we can't do that, forever. And in particular, computers can't do that because computers don't have eyeballs, and don't let any computer vision person tell you otherwise. So Robinson's contribution to this problem was unification as a way of examining two terms syntactically and discovering by an algorithm a common instance of them. Unification has turned out to be tremendously important and powerful. Of course, we're going to use it in theorem proving, which is why it's here. It's also the basis of Prolog, as you will discover soon enough. It has many other applications in the syntactic world of, shall we say, specialized theorem proving realms, dealing with equations, dealing with constraint satisfaction. And of course, and you are all great fans of the ML programming language, and the way type checking works in ML is by unifying to combine the constraints imposed on variables by the structure of your program. What's going on with unification is really quite simple, at least, well, there are many complications, but at basis it's simple. Here again, I would love to use another projector to go through some examples by hand, but this is not a possibility. So I do my best with the slide here. But these 4 examples are sort of canonical for the kinds of things that happen with unification. May I first point out the obvious, that if the two terms that you are trying to unify look completely different, like f of x and g of y, then they are not unifiable, because f is not g. And please do not answer a question with saying yes if f equals g. So, here f never equals g. And equally, a never equals b. If they were equal, they would both be written a. Okay, so the first example is a very simple case. So we have the outer structures the same. They both have a function symbol f. They have 2 arguments each, of course. Now I am using, as usual, a and b for constants, x and y for variables. Incidentally, in the Prolog world, you will generally see capital letters for variables. But I find that ugly, so I am using the end of the alphabet for variables consistently in this course. So, a is a constant, x is a variable. Unification replaces variables by terms. Of course, it only replaces variables, and remember, the hint is in the name. Variables vary. Constants stay constant. So x can be replaced by a, y can be replaced by b. Bingo, we have made the 2 terms the same as FAB. The crucial thing here, in fact, is not simply that they can be made the same, but that we remember how it was done. So we return from it a substitution saying x has been replaced by a, y has been replaced by b. And this substitution will need to be applied typically to other occurrences of x and y elsewhere in whatever we are doing. So if we are doing theorem proving, there will be other occurrences of x and y in our clause, and we will need to substitute for those. If we're doing ML type checking, there will be other occurrences of hidden type variables within an expression we are type checking, and the constraints from this particular unification will be applied to those other occurrences of these type variables. What about this example here, unifying fxx with fab? Now, intuitively, this can't happen because any common instance of this, fxx means the two arguments will have to be the same. So they could be any term, but it has to be the same term for both arguments here. But the second term we're trying to unify this with has different arguments. And remember, A is never equal to B. So unification fails. This one here is the most important example and the one that will trip you up, so pay attention now. In this example, we again have fxx. The two arguments must be the same. Here we have fy g of y. Now we have a lot of variables here, and yet in the second call to f, you see that g of y involves y, which is the first argument, but with a g stuck on top of it, which means the second argument is syntactically bigger than the first argument. And please don't say, what if g is the identity function? Because g is not the identity function. G is the function that sticks g in front of its argument. Therefore, intuitively, there is no common instance of these two terms. What will actually happen here is it will say, okay, x and y are the same variable, so it might come up here and say this x here is now y. Now I need to set y, I need to replace y by g of y. So I'm replacing y by a term containing y itself, which is not allowed. That is called an occurs violation because y occurs in g of y. The occurs check turns out to be quite interesting in the Prolog language because it is a slow check to perform, which means that Prolog systems tend to ignore it, which means that sometimes your Prolog program can get into an infinite loop during unification, which is an embarrassing situation to find yourself in. Now, this last example is a sort of horrible thing you'll see on an exam in which it's trying to check whether you know how to chase the variables as you unify things successively. It is a bit of a mess to go through, but we can see what will happen here is you can see that the alter symbols are the same. And if I could do this in person in front of you, I would probably say you can use a two-finger method here. One finger on the first term, another finger on the second term, and then you have to correct all the disagreements. So they actually would call these disagreement pairs. So here we can identify x and w. Let's call them both x. That means in particular this w over here will now be x. And if I could draw on this, I would write an x here. Then, for the second argument, we see that x must be a. A is a constant, so it can't be changed. X is a variable, so it can be changed. And now x, and of course w as well, have been replaced by a. Looking at the third argument, we have z, which is still a variable, and it has to match with this thing here, which remember has become h of a. We can do that so the terms are unifiable. And what has happened in the end? W became a, x became a, and z became h of a. Now, of course, I did this in an unbelievably efficient way because we would imagine copying them out, crossing things out, copying terms over, and so on. Of course, this would never be done by a computer. It would all be done by updating pointers. And it's worth mentioning that if you do this naively, your algorithm will take exponential time. Because the exponential case is very rare, most people don't bother to do anything more sophisticated, which means you can make most ML compilers hang basically forever simply by typing in a certain bit of code, which I'm afraid I don't have with me at the moment, but it does exist, a very small piece of program which creates an exponential unification problem in the type checking so that you type in the code and your ML system never comes back to you. Boo-hoo. The trouble is more efficient unification algorithms are kind of tricky to write out, and generally there is no real need for them. Now, finally, we have all the ingredients for sound theorem proving. I would like to go here through two basic examples to try and show you the difference between, shall we say, sound and unsound use of quantifiers. So this first example, this is a theorem. As there are a lot of quantifiers, it's worth explaining what is going on here. So this thing on the left, let's interpret R by loves. So this says there exists y for all x, rxy. This is basically saying there is somebody that everybody loves. Maybe me, right? Everybody loves me. Isn't that so? And if there is somebody that everybody loves, then it clearly follows that everybody loves somebody, which is what it says here, because everybody loves me, right? So this is a theorem. Now let's see what happens through all the processes we've seen so far. We convert this to clauses having negated it. I assume you can do that for yourself. We do the skolemisation, and we get these two clauses right here. And it's a worthwhile exercise for you to check that these are the two clauses you get. And by the way, we have done skolemisation twice. The first time we used A, always a good choice for a constant. Then we used B, almost as good as A, in fact. So we have two distinct constants. You would never use the same constant twice, of course, in skolemisation. Finally, we need to apply our resolution rule, which, as you may remember from the last time, you have a positive and a negative occurrence of the same literal. Now, here we're going to allow unification to mediate so that it's enough if we can unify the two. And by unification, we obtain this unifier replacing x by b and y by a. Now we look at the common instances that we get here, the instances that we get, and they are RBA and not RBA, and there is a contradiction. Now, this example looks very similar to the previous one, but it's not a theorem, and we can see why. So if we look at this case, again, if R means loves, think of everybody loves somebody, is what this says. This could be, for example, everybody loves their mother. Fine. But just because everybody loves their mother this doesn't give us some kind of supermother? Doesn't exist necessarily. So we cannot expect this to be true. By the way, if you see an exam question asking you to give a counterexample to a formula like this, you've got to be a little more precise than talking about mothers. So maybe you could use something with numbers, or at least write things down and be very clear and explicit. Anyway, when we convert this to clauses, they are almost the same clauses as before, but as you can see, where we had constants, now we have functions. And it will turn out that the arguments of the Skolem functions will prevent unification due to the occurs check. So we have this one here, the first atomic formula has Rx of Fx, so the second argument is syntactically larger than the first. With the second occurrence of R, it is the first argument, g of y, which is bigger than the second argument, which is only y. So we can see that they're not going to be unifiable, and if you try, you will get an occurs check very quickly. Again, it's a good exercise to try that. Therefore, there is no common instance of these two formulas, and therefore there will be no contradiction found. This formula isn't a theorem.